said, oh, so you'll become a project manager. And I was a little bit offended by this, that he would immediately put me into that box and say, you will become a project manager. Another time, when I was doing holiday work at my bursary company, back home in Namibia, I asked an engineer whether, in fact, he used any of the mathematics that he learned at university. And he said, yes, but sometimes things that you wouldn't expect, like number conversions.
Yes, please start.
And I thought number conversions. I mean, am I spending 4 years at university to learn how to convert meters to kilometers? The sad reality is that many people who enroll for a degree in engineering, because of their passion for design and for solving problems, are sometimes disappointed when they get to industry, and they find that sometimes the real-world engineering work does not entail the in-depth technical design that they were taught at university. And I suspect this is a particularly big challenge in developing countries, such as Namibia and South Africa. Of course, you do find research and development companies that do amazing, interesting, high-tech work, but they're still relatively few and far between. And especially in electronics and telecommunications, they are few and far between. Most telecommunications technologies here are imported. And it's mostly in the defense industry that you do find some R&D companies doing high-tech design work. Unfortunately, I suspect that many, if not most, of the electrical engineering graduates in Southern Africa do not end up doing the kind of in-depth design that they were trained for. For those who do get engineering jobs, many of them end up working as project managers, in procurement, in maintenance and repair. Some basically end up becoming operators, and others are effectively bureaucrats. But if you're lucky like me, you might get a job where you do some basic design work combined with practical installation, commissioning, and maintenance. So when you choose engineering because of your passion for designing new things and solving complex problems, then this reality can be a little bit discouraging. I did not end with my undergraduate degree though, but I continued, and after I finished my undergraduate degree, I started with my postgraduate studies and eventually completed my PhD. And I was lucky that my bursary company gave me 4 years off to complete my PhD, where I specialized in antenna array design. While doing my PhD, I met that same electrical engineer who called me a future project manager, and I introduced myself to him again because he had forgotten who I was. And when I told him this time that I was doing my PhD, he didn't have any comment to make. I also didn't have much to say because I myself did not really know what I was going to do with a PhD in electronic engineering. I just knew that I had a passion for research and design and that I had to pursue this passion, even if perhaps it ended up being a poor career choice. If it wasn't for the fact that I already had employment with my bursary company, I'm honestly not sure how easy it would have been for me to find a job in Namibia as a PhD holder in electronic engineering. And I have to be honest that when I started working for my bursary company in 2019, at the beginning I wasn't too excited about the work that I would be doing. Now, my bursary company is Namibia Water Corporation, or NamWater for short, and I joined them in 2019. I was employed in the communications subdivision where we mainly do telemetry, which is the monitoring of our water infrastructure across the country. Now, Namibia is a vast and sparsely populated country, and we mostly make use of our own UHF or ultra-high frequency radio networks to transfer data from stations across the country, and in some cases also the cell phone network. My day-to-day work involves procuring telemetry components, designing SCADA human-machine interfaces for monitoring these systems, and installing, maintaining, and commissioning telemetry systems. In order to make the best use of the 4 years that I have to work back for my bursary company, I decided to set a goal for myself, and I made my goal to register as a professional engineer, since I felt like I needed a goal to work towards. And I wanted to register in South Africa as well because Namibia is not a signatory to international agreements like South Africa is. I was actually lucky because the kind of practical, hands-on experience I was getting at NamWater was actually perfect for registration. Going through this process of registration, and in particular looking at my work through the lens of the broader engineering skills that you need to demonstrate when you want to apply for registration, it really changed my view of engineering itself. Over time, I had a big change in attitude towards my work, and I went from just trying to do my time, as it were, to really developing an appreciation for the practical engineering skills that I was learning. Before, I had only really thought of engineering in terms of design and discovery. But through my time in industry, I realized that engineering is so much broader than just design. I was always looking for complex problems to solve, but I realized that in a practical engineering environment, the issues that are complex are not always just design issues. While discussing the issue of demonstrating complexity for professional registration, a civil engineer, Robert Blythe, wrote in the South African Civil Engineering magazine, and he said, quote, "There was always a general belief that complexity needs to be demonstrated primarily in respect of the technical complexity of the project. Not always easy to do. Experienced engineers will tell you that complexity covers a much wider aspect of projects and that the technical issues may not in fact always be complex. What about the complexities of social issues, financing, political constraints and policies, economic justification, and other less defined issues?" Even though I do still want to go back into research, recognizing the complexity of engineering in its broader scope really helped me to make the best of my time in industry so far, and to learn some skills that I really don't believe I would have been able to learn any other way. In this talk, I'd like to share some principles that I've learned to help you to go from new to old. And by this, I mean from a high-tech academic environment where you study state-of-the-art techniques to a practical engineering environment where old, tried and tested technologies are being applied. I'd like to share some of the lessons that I've learned in industry and look at the broader scope of the engineering profession. In particular, I'd like to help you to see how adopting the right mindset helps you to get the maximum benefit from your time in industry. The key idea is to realize that complexity does not lie only in design. And the main thesis of my talk today is that simple things become complex in a real-world environment. Simple things become complex in a real-world environment. When you realize this fact, then you will not be bored. When you are actively on the lookout for these broader, complex issues, instead of just trying to get by doing the minimum work required, that is when you really start learning the most valuable practical engineering skills that you can in fact apply almost anywhere in life. But before we have a look at the difference between academia and industry, we first have to step back and ask, what is engineering really? In most countries, engineering is a profession. In other words, a discipline that is regulated for the protection and benefit of society, just like the medical profession or the legal profession. Engineering in this case covers professional, or in some countries chartered engineers, technologists, or in some countries incorporated engineers, and technicians. Practicing independently usually requires one to register as a professional engineer, a technologist, or a technician after completing some years of practical training. And each country has its own standard for evaluating the competence of engineering professionals for the purposes of registration. Countries that are members of the International Professional Engineers Agreement, for example, in the case of professional or chartered engineers, recognize that their standards are essentially equivalent. South Africa, where I'm registered as a professional engineer, and India are both signatories to this agreement. In order to get a definition of engineering as a profession, therefore, let's have a look at the professional competencies as set out by the International Engineering Alliance, which facilitates this agreement. Now, the International Engineering Alliance outlines 13 competencies that engineering professionals must be able to demonstrate. And these competencies are applicable at all of the levels, from professional engineer to technician, but they differ slightly in scope. So I will be giving the definitions for the case of professional engineers. Number one, Comprehend and apply universal knowledge. Comprehend and apply advanced knowledge of the widely applied principles underpinning good practice. Number 2, comprehend and apply local knowledge. Comprehend and apply local knowledge. Comprehend and apply advanced knowledge of the widely applied principles underpinning good practice specific to the jurisdiction of practice. Number 3, problem analysis. Define, investigate, and analyze complex problems using data and information technologies where applicable. Number 4, design and development of solutions. Design or develop solutions to complex problems considering a variety of perspectives and taking into account of stakeholder views. Number 5, evaluation. Evaluate the outcomes and impacts of complex activities. Number 6, protection of society. Recognize the foreseeable economic, social, and environmental effects of complex activities and seek to achieve sustainable outcomes. Number 7, legal, regulatory, and cultural. Meet all legal, regulatory, and cultural requirements and protect public health and safety in the course of all activities. Number 8, ethics. Conduct activities ethically. Number 9, manage engineering activities. Manage part or all of one or more complex activities. Number 10, communication and collaboration. Communicate and collaborate using multiple media clearly and inclusively with a broad range of stakeholders in the course of all activities. Number 11, continuing professional development or CPD and lifelong learning. Undertake CPD activities to maintain and extend competences and enhance the ability to adapt to emerging technologies and the ever-changing nature of work. Number 12, judgment. Recognize complexity and assess alternatives in light of competing requirements and incomplete knowledge. Exercise sound judgment in the course of all complex activities. And lastly, responsibility for decisions. Be responsible for making decisions on part or all of complex activities. When we study engineering at university, we often think of engineering in terms of the first 4 competencies, namely knowledge and problem solving. But the other 9 competencies represent a broader scope of the engineering profession, which can only be developed fully by means of practical experience. In South Africa, for example, university lecturers generally need to do consulting work in addition to the lecturing in order to gain the practical experience required for registration, even though some aspects of lecturing can, of course, count as practical experience, for example, managing a laboratory. But when I started viewing my industry experience in light of these requirements in order to prepare my application for registration, I started recognizing the complexity of these broader issues. And I started realizing that engineering is not only difficult because it is technically challenging, but that it is complex because of all the different real-world implications that need to be taken into account when you practice engineering. I'd like to take you through a few different experiences that I've had in industry so far, and firstly, highlight some key lessons that I've learned, and secondly, also highlight some key differences between academia and industry that one needs to be aware of. Hopefully, some of these principles will help those of you who find yourselves in industry to make the most of your time in industry. The first example from my experience is a proof of concept versus a real-world pilot project. As part of my PhD, I designed a new type of antenna array system. I did not only do a theoretical design, but I also manufactured a prototype, which you can see here. This is a so-called compressive antenna array, where the feed network in the middle takes a 4-element antenna array at the top and produces only 2 outputs or subarrays at the bottom. So I did gain some practical experience in my PhD, but that practical experience was very different from the practical experience that I gained in industry. When I started working as NAMWater, my first task was to design a new server power backup system for our SCADA service, which we use to monitor water supply infrastructure across the country. These SCADA servers are crucial both to short-term water supply operations as well as long-term planning because of the data that we log. Due to poor power quality and reliability in some areas of Namibia, a reliable server power backup system, basically a UPS, was required. And I was given two main requirements. Firstly, that this system should be able to provide backup power for at least 2 days to give enough time for somebody to travel to site to fix any issues. And secondly, that the backup system should require minimal human intervention and it should be able to be monitored remotely from the headquarters in the capital Windhoek. So the idea was simple. Connect off-the-shelf chargers and inverters to off-the-shelf batteries. And compared to my PhD that I just completed, I mean, I thought, wow, this is a really, really simple assignment. However, the requirement of reliability made this project much more complicated than I initially thought. To start off with, I proposed a redundant system made of two independent backup systems. This meant that the servers would not go off if any one single component failed, but it also meant that you had to monitor every single component. Otherwise, you wouldn't know if it had failed. So everything had to be monitored in detail. The mains power, every circuit breaker, every earth leakage relay, every charger, every inverter, every battery cell, every Ethernet, a gateway and switch, even the ambient room temperature. And in total, I ended up monitoring 113 different variables, including 19 different voltages, 12 currents, 8 powers, 7 temperatures, 16 different states, and 45 individual alarms. So even though I was only connecting off-the-shelf devices together, integrating devices from different brands posed significant challenges. For example, there was no easy way for me to determine whether the batteries were still connected because the battery could not tell whether its circuit breaker was on or off, and so it couldn't communicate that information. And there was no easy way to customize the battery because we would have voided the warranty. So the chargers would ensure that there was always a 52 volts on the DC bus, and so you couldn't just check the battery voltage either. So I developed a procedure where it's an automated procedure where the chargers are switched off alternately once per hour for 1 minute in order to test whether a battery voltage is still there on the DC bus. So there were therefore more than enough interesting challenges, even though I was simply connecting devices together. And the incredible level of reliability required goes back to the importance of the SCADA servers. I mean, we definitely don't use this kind of extensive backup system for any server. And these servers that we are backing up are crucial to the short-term water supply operations, as I mentioned, for example, remotely starting and stopping pumps, as well as for the logging of data, which is crucial for long-term planning. And so I therefore had to develop an appreciation for the impact of this engineering activity of mine, which falls under IEA competency number 5, evaluation of impacts, and number 6, protection of society. While I was reading through the Engineering Council of South Africa's documentation, I kept coming across this word sustainability in the context of several different competencies, including engineering knowledge, evaluation of impacts, protection of society, and even decision making. And I thought, how does sustainability come into play in my work? And I realized that a sustainable design in this case meant not making a design decision to use a particular component that might be unavailable in a few years' time and that would necessitate a major design change, as that could be very costly a few years down the line. And this is particularly important when you take into account that the design service life of this backup system was for at least 10 years. So I had to choose components today that I knew would be available in up to 10 years' time, or at least for which there would be alternatives available in the next 10 years. And already this has been tested. Since I installed the first pilot system a year and a half ago, the particular battery model that I chose was discontinued. But luckily, I could easily replace it with another one because I chose standard 19-inch rack mount batteries, of which there are many available in the market. Now, the 19-inch server rack format has been used for the last 100 years, and it allows modular enclosure layouts. The logger that is central to the design will also be discontinued soon due to the global chip shortage. But again, I will easily be able to replace this since I used the industry standard Modbus protocol for getting the information from all the devices. And the Modbus protocol has been around for 40 years. The least flexible design choice I made was the choice of brand for the chargers and the inverters. And I chose this brand because they had 50 years, almost 50 years of experience in developing chargers, inverters, and other similar equipment for remote and rugged environments. And this was important because I would not easily be able to use a different brand with the level of monitoring that I had. So do you see how the word old is coming into play here? Reliability is ensured not necessarily by using the latest and the most modern and innovative technologies, but rather those old standards, those old protocols, and those old companies that have demonstrated themselves over decades. The battery chemistry used is the latest in terms of commercial, what is available commercially, but it's still a mature technology that was first proposed 26 years ago. However, it was not only in the design of the project that ended up being more complex than I thought, but also the management of the project. And this falls under IEA Competency 9, or Manage Engineering Activities. In this case, I had to manage the procurement, which included over 100 unique components, the workshop assembly, the site installation with a team of artisans, the commissioning, the initial maintenance, and now the rollout of the design to multiple server sites. So let's look at a few differences between my PhD prototype and this server backup system. Firstly, the scope of the compressive array was a proof of concept, whereas the scope of the server backup system was a real-world pilot project for one location followed by medium-scale implementation to multiple locations. The maturity of technology used in the compressive array was experimental, and the point of the prototype was really just to demonstrate that a theoretical idea could be feasible to implement in practice, whereas the server backup used mature technologies that had been proven over decades. In terms of the components used, the compressive array used a custom-designed PCB, whereas the server backup integrated off-the-shelf devices. Not even components, but complete devices, which presented its own challenges due to the lack of customizability. In terms of volume, the compressive array was a single prototype, but the server backup system was a single pilot project which will be rolled out to 15 sites, which is still relatively small. Now, importantly, there was no service life associated with the compressive array. It literally only had to work once during testing, and I even used a bare copper finish since I knew that the device would not be used again, instead of using an anti-corrosion finish, for example. On the other hand, the design service life of the server backup was more than 10 years. The compressive array had no requirements in terms of reliability, whereas the server backup system was expected to have a mean time between failures in the order of years, which means that it should only fail every few years at the least. You can see, therefore, that as volume and reliability requirements go up, the challenges move from having to do more with the fundamental technology itself to having more to do with the implementation. And this brings us to our first lesson. A simple design becomes complex when designing for real-world implementation. That goes for both the design itself and managing its real-world implementation as a project. The first key difference, therefore, is that prototypes are technologically complex, but real-world designs are complex in implementation. So this is our first key difference between academia and industry. Prototypes are technologically complex, but real-world designs are complex in implementation. I highly recommend Mike Golio's article, Technology, Maturity, and Other Hurdles, from a 2020 edition of the IEEE Microwave magazine for an insightful overview of the spectrum from proof of concept to mass manufacturing. That's Technology, Maturity, and Other Hurdles. The second example from my experience in industry is about collaboration across domains. At the end of my first year in industry, I had the privilege of working on the telemetry component of a containerized reverse osmosis water treatment plant. The plant was installed by a contractor, and it was my responsibility to connect it to our SCADA HMI system. I had to develop a human-machine interface so that we could monitor the plant remotely. And the HMI is a page that gives you a graphical overview of the plant and shows all the key measurements. At that stage, I knew nothing about reverse osmosis technology or process engineering. And I even struggled to read the process and instrumentation diagrams, the drawings that show you how all the components and instruments are connected. So I had to learn about these processes so that I could draw that HMI page accurately. And by the time I went to site, when the process engineer wasn't there and the technician was struggling with something, I could actually explain a part of the process to him. Even though a chemical or process engineer might consider the workings of a reverse osmosis plant as simple, it was complex and interesting for me simply because it was from a foreign domain. It was from a field that I knew nothing about. And this taught me our second lesson, that a simple concept becomes complex when it's in a foreign domain. By this, I simply mean that something might not be at the forefront of technological innovation, and yet it can still be interesting and complex for you if it's something new for you. So if you find yourself in a work environment where your own work is not that stimulating for you, then look further and be curious about other domains. If you're working with someone on a project from a different discipline, even if you're speaking to your HR officer or an accounting officer, be curious and ask questions and use the opportunity to learn something new and make life interesting. For them, what they are doing might be old news to them, and what you are doing might be old news to you. But to one another, you have the opportunity to learn and to teach something new. Industry often provides unique opportunities for collaboration across different disciplines, which speaks to IEA Competency 10, Communication and Collaboration. When I commissioned the reverse osmosis plant with a process engineer, I honestly had so much fun, even as we sat almost until midnight to commission the system. And that just goes to show that collaboration also gives you that human connection. This brings us to our second key difference between academia and industry, namely that research is more specialist, but industry is more generalist. Now, of course, there are opportunities for collaboration in academia as well, and you can apply these same principles there. But in general, industry teaches you a broader range of skills which can be extremely beneficial further down your career path. For those of you who are in academia and perhaps frustrated by an environment that is too specialized, then my other ambassador talk, From Old to New, talks about how being both a specialist and a generalist can benefit your research, and how even in an academic environment, having a broad range of interests is not always a bad thing. The third example from my experience is about assessing alternatives in the light of real-world requirements. At each of our radio frequency or RF outstations, we have a radio connected via a coaxial cable to an antenna and some RF components in between. And in order to do maintenance and fault finding on these RF systems, we used to use what's called a watt meter or an RF power meter. And now this is an analog instrument that you place somewhere in line along the RF system, and then you can measure the power being transferred in the forward direction and also the power being reflected back, which could indicate a potential issue. Now, I was tasked with replacing all of the old watt meters that had broken. And the ones we used to use appeared to be rugged, but we found that in actual fact, they were prone to damage in the field. And so I decided to consider only alternatives that were rated to the mil-spec PRF 28800F Class 2 environmental specification, which is a measurable way of confirming that a device is suitable for rugged environments in terms of shock, vibration, and temperature, for example. And I decided to go for a cable and antenna analyzer, which is a more advanced form of test instrument. And it's basically a one-port vector network analyzer that allows you to do what we call a line sweep from the ground, which you can then use to pinpoint exactly where the issue is. and at exactly at which distance there is an issue from a single measurement on the ground. You don't even have to climb any towers. So I basically needed two components. I needed a power sensor to measure the power of the radio, and secondly, I needed a cable and antenna analyzer with this line sweep, or what we also call distance to fault capability. Now, many cable and antenna analyzers have an inbuilt power sensor, but it usually has limited accuracy. Up to that point, we specified during our maintenance visits that the power from the radio should be correct to within plus minus 10% or plus minus 0.4 dB. But the internal power sensors available in the cable and antenna analyzers were typically only accurate to about plus minus 1 dB. So I looked at more accurate external power sensors that could be used alongside the cable and antenna tester, but they were quite expensive and sometimes more than half the cost of the cable tester itself. And also, I could not find an external power sensor that was rated to this mil-spec environmental specification that covered our frequency range as well. So there was therefore no solution that met the conflicting requirements of the high sensor power accuracy as well as ruggedness, and I had to choose which one to compromise on. So I had to take a step back and think about whether the required specification we had for the power accuracy of plus minus 10%, if it really addressed our need. The need was not to accurately measure RF power on site, but simply to confirm whether a radio was still in good working condition or not. And for this need, an accuracy of plus minus 1 dB is actually more than sufficient. And so I chose a rugged cable and antenna tester with an internal power sensor, since this met our actual need. And this brings us to our third lesson, namely that a simple choice becomes complex in light of conflicting real-world requirements. Purchasing a new test instrument at first, again, seemed like a very simple task, but the real-world requirement for a rugged test instrument made the whole task significantly more complex, and it actually took me a long time to reach the chosen solution. This decision required judgment, which is defined by IEA Competency 12 judgment as including recognizing complexity and assessing alternatives in light of competing requirements. When you study engineering, you might think that at its core, engineering is about complex mathematical calculations because of all the maths you learn in undergrad. But I think that in actual fact, the process of assessing alternatives and making decisions informed by engineering principles, whether design decisions or other types of decisions, is really what's at the heart of engineering problem solving. And in order to do this properly, an incredibly important skill is being able to identify the real need that informs the requirements and the specifications. As engineers, it's almost like we are wired to jump to solutions, often before we even understand the problem properly. And this tendency of ours to immediately start identifying solutions is both our strong point as well as a weakness that we need to be aware of. In my case, I was searching for a power sensor accurate to plus minus 10% without ever stopping to think where that specification came from and how it related to the actual need. It would have been a very poor design decision to compromise on the requirement for ruggedness in favor for a power sensor that was more accurate than we actually needed. In industry, therefore, it is crucial to understand the need and to make sure, as Jeffrey Pinto would say, that you are dealing with a need in search of a solution and not a solution in search of a need. This is a much more important consideration in industry than in academia, where there is more freedom to explore research questions simply because they are interesting. Often in research, you discover a solution before you even know what problem it solves, and often that's how technology progresses. But unless you are in a research and development environment that specifically gives you freedom to look at topics based on your curiosity, then in industry, you need to discipline yourself to focus on the real need and address that. The third key difference between academia and industry, therefore, is that research is solution first, industry is problem first. That is, Research focuses on developing new solutions because they are new and interesting, but industry focuses on solving real-world problems, and you are unfortunately wasting time and money if you're not addressing the real need. Of course, this is somewhat oversimplified, but it just expresses a difference in focus between academia and industry. My last example from my experience in industry is about making judgments under real-world conditions. Early in my time at NamWater, I had to design an ultra-high frequency or UHF radio link where the telemetry station was located about 47 kilometers from the repeater. So I used Pathos 5 software to analyze the link. I chose a 12-element Yagi antenna at a height of 8 meters. So that is a container with a 6-meter pole fastened to its side. And when I did the calculation, the predicted signal strength was excellent, with a fade margin or margin of safety of over 25 dB. However, when I wanted to go for installation, a colleague of mine questioned my design and he said, will your antenna really be high enough? Because stations in that area struggle with communications. And I found this quite surprising, but I delayed the project until I could get more clarity. I sent somebody to site to do some field tests, and they were worse than I expected, but they were still borderline and therefore inconclusive. I had to decide what to do because the project was being delayed. I could not simply use a longer pole since a container would not be able to sustain or support a longer pole, and a longer pole would require a concrete base, and the civil engineering department also advised that guy wires would be required for fastening the pole. So in the face of incomplete knowledge and a project that was being delayed, I decided to continue according to the original plan and install the antenna as per the original design. And my justification was that the potential benefit of it working outweighed the cost of having to take it down, which would not have been very complex. And that it was worth trying considering the additional cost and time delays of having to investigate an alternative solution. So I installed the antenna as originally planned, and although the performance was worse than expected, it was, at the end of the day, acceptable. After this, I had to try and figure out why there were such huge discrepancies between the calculations and the field results. In this case, the measured signal strength was about 15 dBs worse than expected, which is a huge discrepancy. After a lot of investigation and studying, I realized that diffraction was probably the only mechanism that could produce errors of such magnitudes. The link in question here is not line of sight, but there's an obstruction close to the station, which means that the radio waves reach the station by actually diffracting or bending around the obstacles. So one possible factor is the fact that the calculations only take into account the vertical cross-section of the path profile and do not consider obstructions on the horizontal plane that are not in that path. In this case, the station was located right behind a reservoir on a hill, and the path just grazed the side of the hill. So the peak of the hill was not taken into account into the calculation. When I did an area study where you map the signal reception in the whole area from the repeater, I found that there was an area right next to the station with poor signal reception, and that our station was located right on the edge of that boundary. So I therefore recommended that we not rely on point-to-point designs only, but we always do an area study to look out for adjacent areas of poor reception. There were also some other discrepancies I had to consider. The digital terrain models we use are SRTM or shuttle radar topography mission models, which are radar models generated from space. Now, our repeater in this case was installed on a tower that is existing, and it's 275 meters high. And that was actually picked up by the radar. And in the terrain model, you actually find a hill that's 40 meters high, which obviously doesn't exist in practice. And even next to the station, there was an unrelated telecommunications tower that resulted in such a false hill 9 meters high. And so I had to manually remove these hills from the models used in the calculations. This example shows the importance of understanding the assumptions behind theoretical models and also the effect of the quality of your input data. and not just blindly using an algorithm. So I would like to highlight 3 lessons from this experience. Lesson 4 is that a simple calculation becomes complex when ideal assumptions don't hold. Sometimes it's only in the real world that you discover assumptions that don't hold, and you might never have known about these issues if you only worked with theoretical models. The corresponding key difference is that theoretical models are based on assumptions. Real-world phenomena do not always obey these assumptions. Of course, you can and you should investigate real-world conditions in academic research, but often those in industry are in the best position to identify real-world challenges. And that's why collaboration between academia and industry is so important. The 5th lesson is that a simple judgment becomes complex in the face of incomplete knowledge. And this refers back to IEA Competency 12, judgment, which specifically mentions assessing alternatives in the context of incomplete knowledge. The key difference between academia and industry here is that unanswered questions in research are future work, whereas real-world decisions in industry need to be made despite unanswered questions. And this is one of the key reasons why industry experience is so valuable. Judgment is really developed when you are forced to make a decision despite not having all the required information. In academia, you will often be able to rephrase the problem if you don't have all the answers, or you can leave some unanswered questions for future work. But in industry, decisions need to be made, whether you have all the required information or not. And this is how you develop sound engineering judgment. Lesson 6 is that a simple decision becomes complex when the consequences are real. And with this, I'm not referring to the judgment itself, but the execution of a judgment and a decision and taking responsibility. The key difference here is that poor judgment in academia has indirect consequences, whereas poor judgment in industry has direct consequences. Now, of course, poor judgment in research can have devastating effects, but often those effects are more indirect. It's incredible how difficult it can be to follow through on a decision when the consequences are real. And this personally has been one of my biggest struggles in industry. I hate uncertainty. And when I have to make a decision where I feel like I don't have all the information, it can be paralyzing. It's like there's a mountain in front of you, especially if mistakes are expensive in terms of time and money. And making that decision and accepting the consequences takes real courage. Now, I can't tell you how to learn courage, apart from the simple fact that you can only learn it through experience. And I think this is by far not only one of the most challenging aspects of industry, but also one of the biggest advantages of industry experience, that you get to practice your decision-making muscles and you learn the courage to follow through on your decisions that have significant consequences. Let's go through our lessons one last time. A simple design becomes complex when designing for real-world implementation. A simple concept becomes complex when it's in a foreign domain. A simple choice becomes complex in light of conflicting real-world requirements. A simple calculation becomes complex when ideal assumptions don't hold. A simple judgment becomes complex in the face of incomplete knowledge. A simple decision becomes complex when the consequences are real. In conclusion, when you consider the broader aspects of the engineering profession, you realize that there's a lot more to learn in industry than just design. In fact, many, if not most of the skills we talked about today can be applied to any kind of problem solving, not just engineering design. My challenge to both academics and industry professionals, both specialists and generalists, is to come together and learn from each other. I realize how lucky I am that the experience that I'm able to acquire at NAMWater is uncommonly broad, even by Southern African standards. But I hope that some of the lessons I've shared with you today will help you to identify those opportunities that you do have in your field. and help you realize that the simplest of tasks in a real-world environment are often more complex and more interesting than you might think. If there's one thing I've learned, it's that there's always something to learn. In my other talk, From Old to New, I focus on the lessons that I learned during my PhD, and in particular, how to apply new ideas to an old and established research domain. And I also reflect on the advantages of having a broad range of interests, even as a specialist. Please follow the IEEE Antennas and Propagation Society Young Professionals page on LinkedIn for upcoming talks by myself and other young professional ambassadors. And please feel free to invite me for my other talk. Thank you very much.
Thank you, Dr. Heinrich. That was a beautiful talk. So I have a few rounds of questions for you before we take the questions from the attendees. So attendees, meanwhile, if you have any questions, please raise your hand. Sainath, please let them as a panelist so that we can unmute them. So yeah, before we take questions from the attendees, so we thank you for the wonderful talk. So you have beautifully portrayed through your PhD work. So how to implement things in a real time, and what are the challenges you have faced while implementing in the real time. So, yeah, I have a few rounds of questions like for you, just as a discussion. So what are the some like you have developed some prototype kind of thing. So sorry, design kind of thing. So when you were trying to implement in the real time, like is there any moment like where you have missed the major whole thing which you have not included in the design or something? So is there anything such things you have encountered? So we might have missed a large portion.
You mean that you made a big mistake?
Yes.
So that's always the fear, and like I said at the end, that is, I mean, that is the thing that's always in the back of your mind, and that's the thing that's haunting you every day. When you go to bed, you think, oh, what if I make a mistake? And the problem with that is that it gets to the point where you don't want to make a decision because you're afraid of making a mistake. And like I said, that's really the biggest challenge. And you need to develop confidence. And the thing is, the problem is that you're working with, I mean, for example, if you look at just the budgets, I mean, you might be working with something that costs, I mean, you might be measuring things in terms of, oh, that's my car that just broke there, or, you know, that's my house. I mean, we're just busy looking at some old radios that were broken here, and the cost is it's immense. I mean, you can't even compare. So that really can be paralyzing. But the thing is, you need to learn that even if you make mistakes, it's not the end of the world. Many people have made mistakes. So that's the first thing to realize. It's not the end of the world, and there is scope for you to make mistakes, and everybody will make mistakes, and it's okay. You know, it's a company. It's not you. It's not your money. You know, even though it feels like it's your money, but it's a company, and there are, you know, they do have contingencies in place to account for that. But then the second thing that's very important is obviously you need a good mentor. And in my case, it's very important to have a good relationship with your senior, because you should be working under somebody, and to go to them, and you know, sometimes you also feel stupid for asking a question, but you shouldn't. You should also always have that relationship as open as possible. Have somebody that you can go to and say, look, I'm unsure, can you please assist? And not be afraid to ask questions, because sometimes I also find that the challenge is you try to do things on your own and you don't have all the knowledge, and you're too proud to go to somebody else and ask a question. So the first thing is to realize, you know, people do make mistakes and it's okay. And the second thing is that you need to have a good relationship with your mentor.
Yeah, thank you. So the next question is a follow-up question on like what we have talked now. So regarding uncertainty. So in the research, so we always include uncertainty like in the error bars, and if it is like little more, I mean, we just include it. Okay, this can be of within this step. But when we implement it in the real time, so when we go to the real world, this error bars plays a huge role, I think. So even if it is like a minute variation may cause like a huge loss, or like may have a huge impact on whatever prototype we develop or something. So how do you like deal with these things?
You do deal with them, but they're not always as quantified as in research. In research, there's always a number. You always have to have a number. And in industry, it's not always like that. You often have to make a decision without, like I said, without having all the information. And sometimes you need to know, and that's what's so difficult. Sometimes you need to make a decision even though you don't know exactly what the range of that error bars is. But then you have to make sure that there's a margin of safety. So for example, with the backup system, I mean, we design for things breaking. That's what we do. Because of the reliability, in all our systems, there's redundancy. So if you design, for example, I have a redundant system where if one component fails, there's a backup one ready. Then, predicting exactly when this one is going to fail is not really as important as having both in place. So you could go into modeling exactly what the mean time between failure is for every single component, but in industry, that's not necessarily the focus. The focus is just to make sure that that redundancy is there. So you know that if something fails, then there's one that can step in, and then there will be continuity, and then you can replace that one. And so that becomes the focus. So it's challenging. It's not always, and that's also what I found difficult moving from academia, because I'm so used to everything being so well defined. And if there's something that you're not sure of, you go deeper and deeper and deeper until you get an answer. But you'll be wasting your employer's time and money if you do that, because they don't necessarily pay you to go so in depth. They pay you to make it work. And so that can be especially for somebody who's done postgrad, who goes into a very practical field like I have. I think perhaps in the R&D environment, it's a little bit different, but in a more practical engineering environment, you have to learn to think a little bit differently. But at the end of the day, having both perspectives really, I think, it really it helps you to be a more well-rounded engineer at the end of the day.
Yes, yes, absolutely. Yeah, so one more, I have one more question. So you have mentioned this research is more specialist and industry is more generalist. Yeah, that is true, because we have, when we are in this research, we have already narrowed down to a very specific topic. So from the undergraduate to masters and to the graduate. So how do you scale it up? Because we are already in a more specialized, very very more specific domain. So how do you scale up and and go to this generalist domain, like where you have to learn like many other skills also?
I think you just have to go there. You have to. That's why my story is so unique, because I never expected to go from have these two opposites. So sometimes you just have to go and you know find that opportunity, and even if it's perhaps less specialized, then maybe go to, even if you just do like an internship or something to get that broad experience. You have to be in that environment. Um, and in terms of the mindset, I think some of the things I mentioned could help you to adapt your mindset. But when you are there, and you will be forced to do that. It's you will have your tasks, and you'll be forced to think differently, and you're forced to have to take a broader approach, just simply because your work is so much broader. I mean, if you're doing in my case, you're doing a lot of the project yourself, and that is actually really a privilege. And I'm not sure how that is in India and how that is in other countries, but I think that is an advantage actually of a developing country, where you have less specialists in general, and so the people that are there are forced to do more. And so if you can have the opportunity even to get an opportunity like that, I even thought of including in part of my talk, that perhaps even between developed and developing countries, there needs to be a conversation to even perhaps like an exchange program. I know, for example, that we have doctors coming from Europe to South Africa because they get specific experience there that they just don't get in Europe. And so perhaps one could start that conversation and see, where can we share these skills, because it's not everybody who gets necessarily that opportunity.
Yes. Yes, Dr. Hendrich, thank you. Yeah, that's a great idea also, because maybe people in the developed countries may not have this opportunity of getting everything from the scratch, and maybe we will have more opportunities to work everything and to see everything how it works. Yeah. So, yeah, that was a very beautiful talk. And is there any questions, Final? Okay. Okay. Akhila, yeah, you can unmute yourself and you can ask, I think.
Hello.
Yeah, hi,
Hello.
Akhila.
Am I audible?
Yes, please
Yes.
go.
Thank you, Dr. Heinrich, for a beautiful and informative talk. And you explained it a lot about the difficulties. But I have a simple question. What are the most common difficulties that an academician facing when they are moving to the industry? Common difficulties.
Probably by far the biggest challenge is, look, in academia you are, especially in postgrad, but even as a student, as an undergraduate student, you learn to think in a specific way where you do everything. If you think of, let's say, if you think of writing a research paper, right? You don't leave any stone unturned. Like you really strive for perfection. If you have a question, you have to understand that perfectly. But in industry, it's not like that. You don't have the time to go into everything as deeply. So that's really a challenge, to change your mindset, where you need to learn to be okay with uncertainty, and need to be okay with not understanding everything. Like, for example, that example I gave of um, the the link design that I did, and trying to do the calculations and then not understanding why. I mean, I really want to go deeper and understand exactly why in this case it didn't work. But I don't have time to do that all day, because that could be a very long investigation. So the biggest challenge is just to I think, make peace with the fact that sometimes you can do a half work, and that's fine, and accept that, and not feel guilty for feeling that your work, that you did now half work, or you didn't do it properly. So for me, at least, that was the biggest challenge, to change my mindset. In industry, you need speed. You need to be making decisions. You can't stop every time and think. You need to move, and that's been a challenge for me.
Thank you, Dr. Heinrich. So can you suggest a few things that we can train from the beginning so that it can be easy? Few common things that we can train ourselves.
Can I just repeat that?
Uh, Give us some suggestion that from the beginning we can train ourselves to meet the industry, meet the demand of the industry.
Yeah. I think if you go back to those competencies set out by the Engineering Alliance, and your specific ones for your country as well, um, what worked for me was when I started work, to aim for registration, and then as a byproduct, I learned so much, but it was because I approached my work like that. Because what I find is that you often do something, but you don't realize. Let's say you're making a complex decision, right? You make the decision and you make a good decision, but you don't always stop to think about what you just did. And sometimes, if you just stop and reflect, on what you're doing, then that already helps. So I would say start with those, competencies, and start, just take maybe once a month and do a review, and then just sit and just look at your progress. And I think that is something that a practical thing that's very useful, to make sure that and then sit down with your mentor, and then, just have a look at how you're doing in all those aspects, because sometimes you miss something, maybe ethics, maybe,
Yes, yes.
impact of, maybe you're not focusing on everything. It's 13, it's a lot, so it's a lot to focus on. So it's good to sit down maybe once a month, or every once a quarter, and then, just reflect on your work with your mentor, and see where you are. I think that's something practical that really helps.
Yes, yes, yes. Thank you, Dr. Heinrich, for the answer. Thank you very much.
Thank you, Akela, for your question. That was a very good question. And we have one more question from Siddhant. So I'll read it out. How do you think a cross-departmental idea of things, such as having an idea of HR and accounting work, helpful for an engineer in an industrial setting, or maybe in general?
Can you just read that one for me again, please?
Yeah. So how do you think a cross-departmental idea of things helpful for an engineer in an industrial setting? Like, so because I think so, Siddhant. So if you are in the attendees, can you unmute so that you can better explain this? Hello. So maybe I can rephrase this question. Hello, Siddhant?
Hello.
Yes, Siddhant, can you go ahead? Hello?
Okay. So
Yeah.
am I audible?
Okay.
Yes, Siddhant.
I, I think I've got it. I just read it here in the chat. Yeah, I think I understand the question now.
Okay.
Yes. How do you think? Okay, so that basically, yeah, that's basically the principle of having
Yes,
a
it was
broad range of
departmental
interests.
ID helps me.
Hmm.
I think so. His network is not that good.
Okay, but I think I got the question.
Yes, please go.
This is a general, this is obviously the first thing is getting an idea of maybe another technical domain, like in my case, process engineering. The benefit there is more obvious because you might need that in your work. You might come across that. So when you're working in a project in the real world, you're never working in isolation. What you're doing is part of a biggest project. So you're not just working, if you are a communications engineer or antenna engineer or whatever, it doesn't matter, but find yourself within a context. And so if you have a working knowledge of other domains, it helps you to understand the requirements that you get better. And so it just makes you more effective. But it goes further than that. It's also a general principle of just being curious. And I think you have to come to my other talk to hear more about that. But it's when you have a general curiosity, then it actually is a benefit because that'll often give you inspiration even in your own work. So even if you're talking to an HR officer, you're talking to somebody that's doing something completely different, then sometimes something they say will actually spark an idea that you have that you can apply to your own work. And so to me, that is really a general life skill. That's something that's not just useful for your career, that's useful in life in general, to be curious. And not just to be so focused on what you're doing that you miss the bigger picture. I think it makes life more interesting, and I think it definitely helps when you need to collaborate with others to make you more effective at collaboration.
Yeah, thank you, Siddhant, for the wonderful question. Yeah, it is always beneficial when we work along with a group of people, that too with the cross-departmental people. It will always spark ideas. Yeah. Yes, I think so. There is no more questions from the attendees. Yeah. Thank you, Dr. Heinrich, once more for this wonderful, beautiful, presented talk. So we have learned so many things, like how to transition from academic to industry, and how things work very differently in both the worlds, and how to bridge it both. Yeah, yeah. Thank you
Thank you so much.
thank you again for the wonderful session.
Thank you so much, and thank you so much for inviting me. I'm very glad to be here today to share my talk with you.
Yeah, thank you. So I'm ending the session here. Thank you all the attendees for attending this webinar. So yeah, thank you everyone.